Okay, hello everybody. So today we have uh, we are going to discuss something interesting. Uh, as always, it's about system stack. So let's step back and think a little bit where we are at the moment in this course, right? So if you remember, we start talking at the very beginning of this course, start talking about a high-level overview of machine learning systems, right? So mainly we started by mainly defining what is a machine learning system, what is the difference between what is traditional machine learning, and why we call this course a machine learning system course. And we talk about some of the challenges of these type of systems in practice. And then we had several lectures on kind of governance of these systems. What are the key enablers, or what are the kind of tooling that we need to construct a system in a principled way. If you remember, we talked about these DevOps tools that it facilitates the process of building machine learning systems at a scale. And then after those lectures, we changed the focus to some theory. We started by talking about some fundamental theory of classifications. Specifically, if you remember, we started by perceptron, a very simple classifier, and then we make it a little bit more complex. We talk about multi-layer perceptrons, and then we also talk about based on the intuition that we built based on these multi-class regression, logistic regression models, we build the intuition how we could build a deep neural network based on these very simple models, basically adding a stack of layers to learn appropriate representation that we can feed into these logistic regression models. And then we also looked at a different category of classifiers, naive Bayes, which are basically probabilistic, and we discussed about these differences, right? And now, now we have some intuition about the fundamentals. Then a natural question is that now we know a little bit of like high-level stuff about machine learning system. We also know a little bit of theory. Then how we could implement things, right? This is a natural question, and this is timely because we are starting to think about and work on your project. So asking about implementation is very natural, right? And it's timely at this point. This lecture and a few other lectures we will have is mainly we will talk about what is the connection with the implementation, right? So mainly we call it system stack. This is what we want to talk about, and more specifically about machine learning. I'm sure that you have heard about some of these frameworks that exist out there, right? So from TensorFlow, probably the most popular ones, Theano, CNTK for Microsoft, for example, Chainer, PyTorch, which becomes more popular these days. So there exist many open source framework that people have used a lot extensively, both for research as well as practice in industry. So, and it really depends. It becomes very confusing. Okay, which one should I use? And this is a very nature question. And today we are not aiming to talk about a specific framework, because this is beyond this course. There are loads of documentation, tutorials, like lectures, stuff about these frameworks, right? This is not about this course, right? So we want to understand what are the principles behind these frameworks and how we can make a sense out of it, or what we should know about this framework that help us to choose one over another, and how we could use these frameworks to build the system that we want to build based on the requirements that we have for the system, or constraint that we have for a system, right? And we talked about this constraint a lot, right? So for example, when we want to deploy a model on a mobile, it would be like, imagine that we want to develop a model and deploy it on something like this, right? So this is, for example, a very simple this is called Coral. You can deploy even neural network on this and run your model, get your results. Or obviously this is very small, right? You cannot fit anything here, right? Obviously you cannot fit a deep network here, but there are like different devices. Like this is another one. This is also from Google, one of the TPU platforms. It obviously has higher capacity than this Coral. You can run like larger models here. There are lots of other kind of hardware platform with different spec and with different, memory sizes, CPU computation capability, and so on, that you can use. So we are going to talk about more practical stuff again, but from systems perspective, and with respect to these kind of frameworks. But before we go into some details, I would like to ask, do you have any question about where we are, or maybe about the project? If you want to ask, this is probably a good time to ask your questions.
The only question I had about the project, I had posted an issue about, which was just the setup of it. I think I had issues resolving dependencies, and some of my teammates also did as well. I didn't know if there were setup instructions. I rewatched the lecture for that video, or for that demo, and I think the only thing Ying Meng mentioned was that you would install it with Anaconda and PyTorch.
Yes.
And the requirements. So I don't know. I thought I'd bring that up just.
So you could, right? That's a good question. So you could, you face an issue. Probably yes. That's a good thing that you create an issue for that. Ying will look at it. We'll get back to you. And please do so, right? So this is a good time to go and play with the code. Ying is developing a tutorial for you guys to get you set up so you can start like implementing the system you want to build, right? More easily, and hopefully this tutorial, I'm sure that this would be very, very helpful. Obviously, it would maybe is as detailed as makes in a point that makes I feel that like it may make some of these tasks very trivial for you, but that's fine. we aim to learn, and that's the goal of this course. But then you may need to more focus on the creativity part, right? So come up, surprise us. That's what we expect you to do. Any other questions you want to ask?
I have one small question.
Okay, go ahead.
So in the past, I worked with TensorFlow, and this course is using more so PyTorch. Do you have any particular reasons as to why this course prefers TensorFlow over PyTorch? I know from an academic standpoint that PyTorch is more preferred, but I've never really understood exactly why.
There is not actually much preference yet. So the research committee now, because of TensorFlow was the first kind of framework specific for deep learning systems. But Facebook recently has spent a lot of effort to make PyTorch somehow even more capability than TensorFlow in some sense, make it easier for developers to write code like faster, more efficiently. And yeah, many researchers now write their code using PyTorch. But they're essentially done, even though you may prefer for some reasons, but really you need to step back and think what is important for you. Whether the kind of system you want to develop, the utility you need, you can find more stable utility in the community of PyTorch or TensorFlow. That's the question you want to ask, and you want to do a little bit of research and to see which one is more suitable for you, because the more stable and more active community, specifically about the project you want to do, you have around the framework, like maybe that's a nature choice. And for Ying, I guess she finds out that she can find more of these utility in PyTorch more recently. Yeah.
Thank you.
Sure. Any other questions? So
I had a quick one.
Yeah.
In the project overview on GitHub and all that, will you add due dates for all the other tasks? And you already talked about task 1, but is that something we can add to the README just so we can keep track of that?
Oh, I thought probably we have to do that for all tasks there. If not, would you mind creating an issue for that? I think Ying had the due dates in her presentation. I forgot, but maybe she forgot to put it in the description. But yeah, if you create an issue, I would appreciate it.
Yeah, okay. Yeah, I can rewatch the presentation too, but yeah, it'd be nice to have them for the next.
Yeah, that's good. Yeah, that's a good point. If we did not mention it, we should. Yeah. Okay, so let's start. So at a high level, if you want to think about system stack for machine learning, or maybe more specifically deep learning, you might want to think about not one layer, but multiple layers of code specifically that take care of different aspects of what you need. At a higher level, maybe you need some API, some kind of library for calculating the gradient, because like in the essential thing, as we discussed, the calculation of gradient for optimization task is important, and like this is a basic utility, the most fundamental utility that you need for all machine learning models or systems. And then at more lower level, maybe you need some computational graph optimization and execution. We'll talk about these, what it means, what are the benefits of that, and some runtime parallel scheduling based on top of these computation graph. Like modern, basically the key idea or the key innovative idea behind these frameworks was really the idea of like, rather than doing the calculation in an ad hoc way, having a model or computation graph based on the calculation or based on the model that you construct. And we will discuss why we need such computation graph and what are the benefits of those at a later part of the lecture. But this layer was actually the most fundamental layers that provide a lot of benefits for computation, especially for machine learning systems. And like the lowest layer, which is more closer to a hardware, you need some sort of, like, for example, kernel code, some optimization utilities, and some accelerators, which are really closer to the hardware, and they're domain specific. And these, the closer you go down and get closer to the hardware, the more domain specific it becomes. The upper you go to this stack, the more general it becomes, right? So in terms of the underlying hardware, and the goal of these stack is to make end user, because previously, if somebody wanted to develop a machine learning system, needed to implement all of these by themselves, which was costly. So they needed to like implement some optimization code maybe for a specific hardware platform that they wanted to run, or doing all of these in an ad hoc and non-principled way. But the benefit of this framework is that it provides these clear-cut boundaries between layers, and you can scale with these layer-wise design. You can really build systems that scale well in a principled way. So let's start by this high-level user API to see what it means, what we mean really, what we have. So let's maybe start by talking about logistic regression, basic model that that we started with. If you remember, we had this input, the input, the xi's coming from this pixel value, and we have extensively talked about that, so I'm not going to spend much time on this. And then we had some way of calculating the intermediate activations, and we discussed about like these weights that we need to multiply to the inputs, and doing some, nonlinear transformation like softmax as we had, in order to make the calculation nonlinear and pass it to another layer and build on top of this, right? But logistic regression was really a very simple, like one layer model that we needed to generate these activations, and we had the fully connected network somehow. So all of these nodes were connected to all the activation, the number of nodes that we needed for activation. In this case, like we had like 10, right? So that was a very simple calculation that we needed for logistic regression. And again, the question is that how we can implement it with something like Numpy, a Python library, right? Numpy is one of those Python libraries that you can use. It provides some facilities for example, matrix linear algebra kind of calculation for you, but it doesn't provide like facilities for calculating the gradients kind of stuff as you get nature from a framework like TensorFlow. So this is a very simple implementation of the same kind of logistic regression model, where we have discussed extensively about the mathematical aspect or theory part of it. So let's see whether we can make a sense out of it, what's going on. So basically, this code defines the model and the kind of calculation that we need for optimizing the model. And by optimization, you know already that we need to find good weights that classify the example appropriately, right? So here, obviously, like you need piece of code to calculate softmax, right? This is what you needed here essentially. Okay, so let's see how this was implemented here, right? So here is the code that really in a very simple but yet elegant way defines softmax using the NumPy C here, NP. So basically it started by importing NP NumPy, and it uses some of the operation that you need, like sum, for example, for a vector, and like some operation, mathematical operator like exponents. And the calculation is really simple, and the code is very much readable. So essentially, this part is the most important part of the code, where you first exponent the input. So you have x. What you need is really to calculate ex divided by going over all elements of x, right? For basically calculating softmax, right? This is what we had for softmax, right? Okay, one thing, right? Again, like one suggestion that I have, like in order to understand and to work out or to implement your code in the best possible way, like it's always good to think about and correspond it with the math, right? This is very important if you want to learn machine learning in the most efficient way. You always need to think when you're writing code. You always need to also think about the underlying mathematical intuitions, and that's really important, right? So, for example, here you see this line of code, right? What it does is really you see that it finds the maximum value of x. X again is the input to this function. Softmax is a function, right? So it goes over all elements of x and give you the maximum value from this vector. And it basically deduct this value from all elements of the vector. Do you know why it does this? And whether it makes any sense?
Is this some kind of normalization?
What kind of normalization it is? And why it makes sense here with this equation?
It's going to make the highest element 0 and all others negative.
Why? Yeah, that's a good thing. Why does it that?
I mean, you're finding the highest one and subtracting the highest one from itself, so you get 0 there. And then in every other case, you're finding something less than that, subtracting the highest, so you get a negative. And so when you take the exponential, you'll get something less than 1.
Right. So so let's maybe ask two questions, right? So why we want to do such transformation, and whether it makes sense. Right. I haven't still yet to listen why we needed to do such transformation, why we don't simply calculate whatever we had in the formula, right? And the formula was really simple. What we wanted to do is really to maybe only like have these 2 lines of code, okay? So why we may needed this? So obviously, like with this, you could get whatever you needed for this equation, right? Is that correct? So if we remove this line of code, whether you would get the same, so this is what it does, right? We really exponent x and they divide it by all of these exi, right? You see the sum here, right? Sum over xi.
Like, is the purpose like an issue of math with like large numbers, just like floating point error or missing like not floating point error necessarily, but like if you're doing these operations with really large numbers, then you might run out of resources, you might have overflow issues. So maybe you try to make all the numbers, I guess, smaller in a sense. I guess that's what this, you're bringing everything to 0 or negative, and I think maybe this reduces that possibility.
Yes, that's a good point, right? So we discussed about like, and you know that, like, I presume you have already a good sense of like the limitation of any computer, right? So you have limited resources to store and execute things, right? And if you have a very large number, like if your x, what were the x's? X is essentially like when we have softmax of x, x is the activations, right? And the activations coming from these maybe giant inner product of W's and your input, right? And this could essentially becomes large. Really depends on your input values and the weights. The value that you feed to your softmax, right? This is the thing that you feed to your softmax. Okay, this might overflow if this is large, right? So because as a part of softmax, you need to calculate the exponent. So if this is large, this could overflow. Okay, overflow, for those who are not familiar, meaning that basically your computer cannot represent this number by whatever representation of your floating point you have, right? Because for any digits in your computer, you have a limited amount of memory, right? Whether it's 32 or 64 bits or whatever. So we can represent a certain real number, right? And this is a simple trick that you want to do in order to avoid this overflow. But the very natural question could be whether we mess around with the math or not, right? Because like we don't want to calculate something which doesn't make sense. And can you tell me why it does make sense in terms of mathematics, right? If there is no volunteer, probably we can work it out together, right? So you remember, like let's imagine like we have like activation Z1, Z2, Z3. For softmax, we have this EZ1 plus EZ2 plus EZ3. Okay. This was the first element. The second element was EZ2 divided by EZ1 plus EZ2 plus EZ3 and EZ3, right? EZ1, EZ2, EZ3. Okay, these are like the softmax calculation. So what it does is that it finds out the maximum it deduct the same value from all elements, right? So imagine in this case, let's assume that EZ3 is the maximum, okay? So what it does is that it transforms this to Z1 minus Z3, okay? Z2 minus Z3 and 0, right? So let's see what happens to this softmax calculation. Really, the first one would become EZ1 minus, so we need to look at this, right? Minus Z3. So for this one becomes EZ1 minus EZ3. EZ2 minus EZ3 plus what?
1.
Plus 1, okay. Same here, right? The last one becomes 1 over, right? Okay, so let's see what we get. How we proceed? So you see that by math, you know how to do things, right? So then it's this becomes EZ1 over EZ3, okay, EZ2 over EZ3 plus EZ3 over EZ3, right? This is the same, okay? So you do the common denominator easy 3, right? So this becomes easy 1 plus easy 2 plus easy 3. This is for your denominator. Here you get also the same, easy 1 over easy 3, okay? And then this one, you get the same magic, right? So basically, by doing this, by doing this transformation, really, you would get the same activation or the same values after you pass it through this softmax. It doesn't matter, right? And this is actually true when you deduct basically the same value from all elements of your activation, right? In this case, we deduct the maximum value, but if you deduct the same value, math says that it doesn't affect this softmax calculation, okay? As long as you deduct the same value from all elements. Again, to build up some intuition, sometimes we need these tricks, but we need to understand why, right? In this case was avoiding overflow. And obviously we need to make a sense whether we don't mess up with the mathematics. We don't want to calculate wrong things. We need to do the math and prove that, okay, we get the same value, the same function value as we expected. We are not getting any incorrect calculation. So even though you could, like, maybe you have a proof that like your input for your activation would have an upper bound, and then you're free to remove this line of code. You won't lose anything if you have it or not have it. But if you have it, it avoids the calculation of when the activation becomes very large. Okay. So, and then here at this line, basically what it does is that you have some examples, right? Examples that was selected here, right? And associated, this is associated labels. This is the your input, right? Access from a particular batch from MNIST dataset, right? This digits dataset, and it selected from it was selected from training examples. And then you calculated this dot product between input and weights, right? Why inputs and weights? How you corresponded? Why we have this?
Isn't that how like you evaluate the score, kind of the weights times the input?
Yeah. So you had the math here, right? So basically, you needed to have a dot product of these weights represented by these arrows and the inputs, right? In order to calculate, for example, for H1, you needed to have these xi's and the associated weights, right, in corresponding to these weights, right? And we discussed about the mathematics to calculate the these activations. So basically, pretty much it does the same thing, right? It's really dot product of input with the weights, and it passes through the softmax, basically what we needed to calculate here to give us the probabilities, right? You remember we discussed about, like, even if we use this softmax, we needed to transform it to some probabilities to make some trade-off and distinguish between good and bad. and this softmax, because of the properties, we then select the highest, the most probable class as your output. Okay, and then once you have these, and what is y in this case? Y is your output, right? Whatever you get from your model. Okay, so this these y's basically tells you the actual class label of your model, right? And then for optimizing, you remember we also had lectures about optimization, right? So far this line calculated the y, right? The class label that the model thinks, right, based on the current weights, right? So here you see W. This is the current weight, right? And you see a loop here because we want to have a mean to update the weight, right? This stochastic gradient descent. You remember we had discussed about this gradient descent, a stochastic version of gradient descent, because of this selecting a batch of example and doing this optimization process in an iterative fashion. Hopefully you remember this, these ideas. And then, so the rest would be, and you see that here, you see really update to the weight, right? So you have this learning rate, which was defined where here, right? You had this learning rate that you defined here. You started with these 0 weights, and then you updated. So here you see an update rule. So you deduct this W grad multiplying by learning rate to derive the next set of weights, essentially doing this update, if you remember. Okay, you remember this update rule, right? So you had this learning rate, and then you needed to calculate the gradient of your loss function or cost function, right, with respect to the weights. And then after multiplying with the learning, you needed to update this the current weight, deduct it, and then update it, and then doing the next calculation with the updated weights, right? This is the way how a stochastic gradient descent actually works. Do you have any question? Is everything clear for you?
Actually, I'm a little bit confused with the code still. What exactly is batch underscore XS and batch underscore YS? I know those are like lists, but I'm a little confused to like what they actually represent.
Right. So you see here. So basically, if this is, let's say,
like I know they're related to the MNIST variable, which I assume is some sort of database you're pulling from. And then with the first, I'd say 1,000 examples you're pulling from it, you're like extracting 2 arrays from it.
Right. So so let's make a sense out of it, right? So here, what you have from y is whatever value you get from your softmax, and you remember from softmax, what was the value you get? Tell me. What was the kind of value you get from softmax? How it looks like? Is it a number or is it?
A fraction.
Is what?
A fraction.
Instruction, what do you mean?
A fraction, a real number.
Right. What we call these numbers?
Probability.
Is what?
A probability
Probability,
number.
right? These are probabilities number, right? So between 0 and 1, right? So, and was it one number or it was a vector of numbers?
A vector of numbers.
Vector of numbers, right? Right, so, and what was the size of the vector? Was it like 2, 300? What was the size of the vector?
It's the size of like the number of possible classifications, right?
Exactly. So the size of y was really depends on the number of classes that you essentially have for your model. So
is this why, I'm sorry, is this why you have W equals NP dot zeros? Because MNIST means like, it's like a database where you have like images of numbers and you try to convert them to a class for numbers.
So in this case, the size should be 10, right?
Yes.
So you have a vector of like, let's say you have some probabilities, right? And the size of this vector would be 10, and each of these could be like 0.1, for example, whatever it is, right? So once you get this y, then you see that the code says that look at this label that you get from here. What are these batch y's? What are these batch y's? Basically, is the true label, right? You get these y's from your training set, and this is supervised learning. So you have this. This is your actual label, the true label that you get from your training set, right? So you have these actual y's, and then you calculate the difference between what you get from your model. Basically, this is the model is the current version of the model based on the current weights, right? Really, the model boils down to the weights, right? This is what we learn. Then you calculate the difference between what you get from the model and what is the true label. And the true label, typically, it is a vector of 0 and 1s, right? So it looks like, for example, if this is digit 8, the true label would be 0, 0, 0, and then 1 for like index 8, or basically depends what you call this index, right? And then 0, and then right. So this is for digit 0, 1, 2, 3, 4, 5, 6, 8, and 9. Okay. So this is a kind of this is how these batch y's looks like, and this is actually a stack of batch y's, right? You have 100 examples. So for both these y and batch y's, they're a stack of vector. But imagine that like this is only one. We use only one example to simplify. So this looks like a vector, and then it calculates the y grad by multiplying the x's, the inputs, with the difference between the actual, the true labels and the probabilities that was calculated based on the model. And it calls it wgrad, and then it uses wgrad for this calculation. Does it make sense?
Yeah, that clarifies a lot.
But can anybody explain to me why we are doing this? And whether because so far we haven't talked about the loss function, have we? Loss function could be anything, right? So the loss function is really, so in general, I mean, if you remember what we have discussed previously, we discussed a function about in the lecture it was called G of W, right? If you remember, some people represent it as J of W or J of, if you also saw J of theta. So theta and W are more or less the same. You can call it G, you can typically LW is more typical than the other notations, or sometimes you see also cost of W, because sometimes it's also called cost function. But at the end of the day is a function that you want to use for this, right? And again, Numpy here doesn't provide any calculation of this gradient, right? But we need to, I mean, if you want to do the same really with something like TensorFlow, you can do it a lot easier, right? So here is doing the same thing using a version of TensorFlow. It's called TinyFlow, but pretty much is the same. You declare these variables, we'll discuss this, and at some point you need to calculate this gradient, right? So here you define your cost function here. Basically, cross entropy is your cost function, which is a function that looks like this, right? Is sum of the log, sum of the, so basically you calculate these y's, pass it through log, and you multiply it by these y's, right? So this is the true y's, the true labels, right? And these y's are the y's that you calculated based on the model itself. And then this is the way how you define it. So mathematically is basically is sum over y log y, right? Or more specifically, you want to distinguish between these y's. So this is the correct label, right? And this is the label that you get from the model. And this is what is called cross entropy, right? Maybe you have seen a version of this for, yeah, here it's defined, right? But maybe you for binary classifieds, it becomes a lot more simpler for such thing, right? So it becomes really so you can represent it as y log log of basically your activation, like this is this sigmoid. And I hope I don't make a mistake. Yes. Yeah, this is okay. Yes, so this is for binary classifier, where you have two labels, either 1 or 0. And then you need to sum over all of your xi's, right? This is the correct definition of like your J of W. Okay, yeah. But pretty much it's the same. This is for the multi-class version of it. So you define your cost function. This is called cross entropy, and then you do the same. Really, everything else is the same, but the framework, what it does is really it's really giving you the gradient by default, right? So you don't need to do any kind of math for calculating the gradient of your cost function or whatever you need. So for optimization, you only need to call this function gradients. You pass it with your function and it gives you the gradient, right? So you now have this W grad, and then you do the same, right? So you update your weights using this update rule. So pretty much the same exactly. Here, like this part you declare stuff, this part you execute the stuff. We'll talk about this, the difference and the benefit of like declaration versus execution. But I wanted you to understand the difference, right, with something that you get by TensorFlow, which really gives you the gradient by calling one function, and what you need to do here, really doing the calculation yourself, and to see the math is really could be. I'm interested if we discuss about the mathematics behind it, but really something that Numpy doesn't give you the gradient. You need to do the math and calculate it. That this gives you this. Basically, this really calculate this line of code, calculate the this gradient of the loss function or cost function, whatever it is, with respect to W. But this line of code could be different if we have had different loss function. Here, this assumption is that the cost function that we define is a cross entropy cost function, right? And we need to do a little bit of math why it makes sense if we do the dot product between this difference between y grad and the transpose. This is the transpose of the x's, the inputs. It gives us the whatever we need. It gives us the gradient of the cost function, right? Because again, the assumption here is that and we might have different kind of cost function for the model that we have, And if we change the cost function, we need to go back and change this line of code for calculating the gradient for optimization process. Does it make sense? Is there any question here?
I'm a little bit lost. Where is the cost function in the Numpy example?
That's a good question, and that's what we need, right? So really, if you think about it, right, for updating this, and that's why you don't see the cost function here explicitly as you see here, right? Here you explicitly define the cost function. This cross entropy is my cost function, and here is how I define it. And then you pass it through this gradient function that gives you the gradient of this cost function. Because if you look at the math, right, here is what you need, right? So basically, you need to calculate basically the gradient of the loss. But you don't really need the loss function itself, right? As long as you have the gradient, you're good to go to update the weights, right?
Yeah, right.
And this line of code really gives you the gradient of the loss. So for as I mentioned, like for this cross entropy loss function, and in order to understand why, basically, why if we multiply x with this so basically what it does is really we multiply x with the difference of what we get from the model and what we get from the true label. And that gives us this dot product gives us the signal, this gradient that we wanted to have. Maybe let's do a little bit of math to understand this, but yes, let's do it, because that's not a bad idea to do it too, because it then gives you an idea of why, and like it gives you some idea like what are the benefits of these library such as TensorFlow that really makes your life a lot easier by automatically giving you these gradients information, right? And we'll talk about automatic differentiation because this is what these library does do basically in practice. All right, so let's maybe start thinking, okay, what we need to, how we need to start off by thinking about this, right? So let's define our model first. And the model is really the logistic regression, right? How we did things in logistic regression, really what we had was like we calculated this, we had some weights, right? And we calculated these by the inputs, right? And this is how we got this how we got these activations, or better call them, let's call them to be precise, maybe ZI. I think it was the stuff, or maybe ZJ to annotate annotate this better, because ice is the vector going over the input space, right? And right. So basically, this is going over all examples that we have, and these are giving us the activation, and we then pass it through the sigmoid, right? In order to give us the probabilities, right? So the cross entropy in this case, when we have such model, the cross entropy, I mentioned it, how you can define it, right? So you can define it as let's call it J of W. You can define it in a precise way, right? Or maybe. Right. Maybe to make things simple, let's consider that we have two classes, right? We have class as we had before, like we had 0 and 1s. Then this cost function becomes simpler. So this is 1 over n, right? And then what you have here is you go over all examples that you have, log, natural log, right? Of these right, plus so this is the way how your cost function is typically defined, right? Sorry, you have 1 minus sigma. Yes. This is basically this is cross entropy cost function or loss function. Both means the same thing, right? So this is a function of weights, right? So this by definition is the function of weights. Why it's a function of weights? Because we know that by definition these activations are parameterized by weights, right? This is the connection, right? And really we want essentially to find W star, okay, to minimize the cost function for us, right? Or essentially better represented, we want to arg mean W. Hopefully you are familiar with this notation. If you are not, please ask. So basically arg meaning that you want to minimize this cost function with respect to your W, find the optimal weights that gives you the minimum value. If this is a minimization, because like the way how we define it, we want to minimize this function, this nasty function, right? And there are some, and again, like we don't have only this cross entropy cost function. There are several different cost function that people came up with, but this by far the most cross entropy is by far the most useful cost function that gives us reasonable results for classifiers, right? This is the way how the optimization works, right? Okay, so far so good, and we know that for calculating for doing this optimization, essentially we also need the true labels, right? Here are the true labels that we require. And obviously we need the inputs, the xi's as well. This is what is implicit in this definition of the cost function, right? And now what we want to really do is to calculate the gradient of this J with respect to W. This is what we want to calculate, or better, it's better to annotate it correctly. Like, since we are talking about the vector of W, this is the right notation, and if we want to calculate the partial derivative of J with respect to a specific weight, like weight is the vector, right? Like, let's imagine Wi, right? Right, or yeah. So we want to calculate this guy, or better calculate with respect to Wi, in order to get a sense how this partial derivative would look like. Okay, then this function definition should be enough, right? This is what we need, right? We need to do some calculation of the gradient in order to make a sense out of it, right? So let's see what we have in order to calculate this gradient, right? Let me remove this because it becomes easier to see things in one page. Okay, so then let's do the math. What we have here is, we know that by definition this doesn't depend on W. Here what really depends on W is what? Is these guys, right? These guys are dependent on W, right? And we need to be careful, right? So this operator would go inside this summation, and it becomes basically 1 over n x, right? Also goes from here, right? And then we have this guy, and then before this we have this natural log. So do you remember what was the gradient of natural log?
Correct.
What?
1 over x, correct?
Yes. So gradient of natural log of x with respect to x was 1 over x. But if we had like log, this is not really in this case. In this case, we have a function of you have a function of you have like function of these x's, right? Natural log of f of x with respect to x was what? Anybody remembers? Come on.
We have the chain rule then, correct?
Yeah, you need to do the chain rule, right? And the result, it would be f of x, right, multiplied by basically derivative of okay. This was basically this is the thing we need, right? So using this, plugging it in here. So we know that by definition, you can right. What you need to you know, or maybe okay, yeah. Let's do this. Let's not get into other stuff, right? Because I wanted to ask why we are whether this why we did this minimization instead of maximization, but that's another question. So then right, so here we have log, so this becomes, so what we need to do is really to 1 over sigma z, right? Are we doing the correct things? Right? Are we? Okay. And then 1 over minus, right? And then doing the same thing with respect to this, right? So here we have this guy, right? So we need to be careful here. So this guy goes down 1 minus sigma z multiplied by so this is our f of x. So we need to be careful here. Minus, we need minus, right? Minus derivative of sigma z with respect to wi, right? And then we have this guy, Let's get rid of these. And then, right, so let's simplify things. We have 1 minus over n, and then sigma x y over the minus right. This is what we have. Okay, is that clear?
Yeah.
Right. And then let's think. So now, so what else? because we need to make sense of that line of code, right? How we want to reach this point, right? We want to see why really this makes sense. And here is dot product of input, right? Excess and the difference between the true label and whatever we get from sigmoid, right? Oops. But we are almost getting there, right? Hopefully. So by looking at this, so one more thing. You need also one more thing to make a sense out of this. Maybe let's focus on this. What this says. So we need to take the gradient of sorry, we went over time, but let's finish this and then we will stop. Make a sense out of this sigma z with respect to the weights, right? And we can really do that because this is really simple, right? So it's a weighted average of the weighted average of the inputs, right? So if we want to take the gradient of this guy with respect to a specific input index, what would be the outcome? Can anybody tell? This is
I think
simple.
it would be only xi, correct?
Right. That's absolutely correct. Right. So basically, you need to know what exactly this index is, and then this is weighted sum. So here it becomes xi, right? So this is the input associated to this a specific weight wi multiplied by this gradient of the sigmoid, right? By chain rule, right? You get this by chain rule. Okay, this is a lot better. Now what we have is, again, let's simplify things. Maybe let's also do this thing. What we have is so basically what we do is we are making the common denominator here, right? This guy and this guy. And then above we have what we get is, let's see, y minus y sigma z, right? Then sigma z plus y sigma z, right? Are we all right, or we did things incorrectly?
The numerator makes sense. What is the sigma prime of z that you added there? What is that derivative with respect to?
Which one?
So you said the partial with respect to Wi evaluates to xi times the derivative of the sigma function.
That's
What is that derivative?
this is with respect to the activation Z, right? You're asking
Yeah.
about this guy, right?
Yeah.
Yeah. This is with respect to Z now instead of Wi. And then this guy with this guy, right? And then we have here is 1n sigma y minus sigma z 1 minus sigma z, right? Yes. So what is the gradient of sigma z, right? Anybody knows? So let's look at the math. I guess we had it in the other lecture slides, right? I remember we had one slide about this in order to make sure. We had it when we talk about activation. Where we talk about activation, it was in here, right? We didn't have the formulas. Too bad. So here is if what we had, right? So basically we had this sigmoid function, this guy, and this is the derivative of the sigmoid, this line. But basically, let's assume that you guys know it, or somebody given you this activation. You can look at. So if you remember, this sigma z by definition was what? Was depends on z. You remember, right? One over. Sorry. Right? This is E minus C. This is the way how you you define this this function, right? And for taking the gradient, it's become oops. What happened? So this guy basically, with respect to z, it becomes this is by definition it's this is given to you, right? And then sorry, timing. And then you simply replace this with here, right? So you see that you can remove these two things because they're same, right? This guy appear here, and what is remaining is 1 minus n, right? Y minus sigma z multiplied by xi, right? Is that clear?
Yes.
And you see that, like here you have, so this is the dot product, right? Here you have the difference between what was y, it was the true label. What was sigma z was the activation, so was the sigmoid of the activations, right? And this was the your input, or it was your specific input, or the input that you get from the current batch, right? And this is exactly what you have here, right? This is exactly what you calculated here. You calculated the dot product of between your specific input, this input x, and the difference between the correct label and the correct label, this one, and the label that was predicted based on your model, right? So again, to step back, right? This is really important to know the difference. Even though in this case, you see that the calculation of the gradient, this guy, was really simple, right? But it was not really obvious, right? So we needed to do some maths to calculate this guy and write code for that. In this case, was simple dot product, so we were lucky. But if the cost function was differently, maybe it looks like different. And if we change the cost function, we really need to go back and change several lines of code to do the calculation, right? But the benefit of like having some TensorFlow like API like this, you only define your cost. You don't need to do any calculation. The TensorFlow does that for you, right? Does it make sense?
Yes, thank you.
Oh.
So just to summarize, that assumed the use of a sigmoid activation. So it's only valid for a sigmoid activation and for that particular cost function. Otherwise, it would be a really complicated computation.
That is only for like cross entropy cost function and sigmoid, right? You see that we use the gradient of sigmoid, and if we replace sigmoid with tangent or something else, some other activation, we have many different activation functions. That doesn't work, right? So we need to do the math again, and we need to calculate the gradient of this cost function again differently, right? So again, this really depends on the definition of this loss. For calculating of this loss, you need the inputs, you need the true label, right? You need also the activation. Type of activation could be differently. You need all of these in order to calculate this loss function, or more explicitly, if you want to define the cost function or loss function, whatever you call it, it's better to represent it that it is a function of not only W, but for calculating this, you also need the true label. You also need the input, right? And activation, type of activation, right? So this is more explicit way of defining your loss function, because we use really all of this information to calculate this actual gradient, this guy. And the rest is obvious, right? So once we have this gradient, the rest is simple update rule, right? It's nothing more than that. So I think we went a lot over time. Sorry about that, but that was useful, hopefully. Let's just stop here. Do you have any question?
When you upload the this lecture onto the link you provide on Piazza, Can you make sure it's not just the first hour and the full hour and a half?
It's not really first hour. I uploaded the full thing. I'm not sure what's going on, really. But I also provided the link to YouTube because, like, after lecture, I also upload stuff to YouTube. Go to the Piazza, you will find the link. Yeah.
Will do. Thank you.
Any other questions? Okay. Thanks. See you soon.